Okay, well, thank you all for being here. This is the last webinar of the Spring 2025 edition, and we've been having quite some success. Here I have a slide showing that indeed our stats are on fire. We had a lot of visitors from, as you can see, pretty much all over the world on our website. We are pretty proud of that. We have more than 130 subscribers on our YouTube channel. Maybe we should start monetizing it. I don't know how much that would give us, but I don't know if I think that all of these subscribers voluntarily subscribe to a Rheology YouTube channel. I'm pretty happy about the number.
Yeah.
And by the way, this is also a reminder for you, for all of you, that you can find all of the previous talks there. So if you're interested, and people have seen they're using it, so that's nice. And with today's class, we've had 23 talks given by very young rheologists, and that's very cool, I think. And 10 classes given by established professors from, again, all over the world. And talking about established professors, it's both my honor and my pleasure to introduce today's class, which is going to be given by Safa Jamali, professor at Northeastern University, who's going to give a talk, a class actually, on applications of machine learning in rheology. So I've been looking a lot for that, looking forward a lot to that, to this talk. I suppose that given the number of people here today, I'm not the only one. So Safa, welcome. Thank you so much for accepting to give a class, and thank you for being here. The floor is yours. And just one small tiny thing. If the audience wants to ask questions, Safa is okay in accepting questions while during the presentation. Just raise your hand or write in the chat, and we're going to interrupt Safa for you.
Awesome. Thank you. Thank you, Michelle. Thank you, Leah, for the invitation. It's wonderful. I This is my first time. So being in the Hitchhikers series, but this seems like an awesome community. So job well done, and I hope this continues for a long, long time.
Thank
So
you.
let me
Thank you.
You should be able
share
to
this.
share. Okay,
On
perfect.
top
Yeah.
of it. Yeah.
Okay, let me just go into full screen mode. And this should be okay. Um, and again, you can stop me and ask questions. The only thing is I'm looking at my slides, so feel free to unmute yourself or type there, and Michelle and Leah can
Yeah.
moderate the session.
Great.
So today, a little bit of a bummer for people who were in Lyon, but this is very similar to what I gave as a lecture in Lyon at European Society of Rheology meeting. Um, General topic of applications of machine learning and rheology, and this is to me a little bit of a crazy topic to talk about because it's almost like if you gave a talk on experimental rheology, right? Where do I start? Where do I end? And it's becoming like that. But machine learning and rheology is not that well spread yet, and so hopefully we can cover some grounds today. And I'll show you a little bit of what we have done in my group, but this is by no means the only sets of applications. There are a lot more. Um, and the pace of development in this area is crazy. So, if I'm missing some of your contributions here, I apologize. And every day there are some really cool works that. Oh, go ahead, Michelle. We already started.
Yeah, yeah. I
Go
mean,
ahead.
just
Yeah,
a funny question to break the ice. Was this
yeah, absolutely.
figure AI generated?
Absolutely, it was. Yeah, yeah, yeah. So
So
this is
what did you
ChatGPT.
ask?
I asked, so this was me working around with the idea of a digital rheometer, right? And where you can flow in data, experimental, but also numerical, and also consider models and unifying generally these type of activities through data-driven methods. So this is perfectly made by And I ask it to be in Matrix movie style. So this is as good as ChatGPT could do, but you know how it is.
Nice.
It is a little crazy. So that's a great question. That sets exactly the stage for what I'm going to talk about. So usually I start with this kind of motivation of why we are doing this and why I started caring about machine learning techniques. They're, selfish, career-driven reasons for it, but really as a rheologist, I'm trained as a rheologist. So the way I look at rheology, I've always felt there are two big issues with our community. One is that we sometimes are a little close as a community, and it's very difficult for outsiders to break in and use our science, come to our meetings and learn from our work and also teach us what they do and contribute to other fields. The other thing is, there is always a disconnect between theory, computation, and experiment. So I'm going to explain what I mean by that. My view for rheology, the classical approach is you always start from a general goal or observation. Let's say my goal is to print a 3D a structure out of a slurry, maybe cement, maybe something. I know this topic has been covered by this seminar series. Or maybe I look at a set of behavior. This is an image from Garrett McKinley's work on thixotropy, or you look at toothpaste. You want to explain what that behavior is. The way you go about this is first you go to your rheometer, the best friend of a rheologist, and you start testing your material. You do this testing for different conditions. These are typical data for something we call thixotropic elastoviscoplastic fluids. And then once you gathered information, you try to develop a theory around it and see why those behaviors show up. For example, this is again from Garrett McKinley's group on TVP. So this is a viscoelastic component, a plastic component that has thixotropy inside. The details of the model really doesn't matter here. But the general idea is that you develop a theory behind it, and then once you have that theory, you go and check that theory using computational or numerical models, and to see if you can recover what you observed in your rheometry. And then once you do that, for example, what's shown in this figure, then you can basically now get that model and solve it for different flow conditions, similar to what you started with. If you wanted to 3D print something, then you want to basically model that geometry. The whole idea is to be able to predict the behavior under those processing conditions. So the general idea here has always been to me, is there a role to be played by data-driven models in unifying these theory, experimentation, and modeling efforts so that there is no disconnect, so that we can actually, every experiment we do makes our modeling a little better, our predictions a little better, right? So that's the general idea. That's the main motivation for anything we've done with machine learning and rheology. The reality is there are so many different ways to do it. So one step back, I want to explain AI and ML as a whole, and especially in fluid mechanics and in scientific communities to set the stage on where we are. We are hearing about machine learning everywhere these days, but is it new? No, not at all. It's been around for a long time. Think you would agree that up to about 1960s, science was either theoretical or experimental. There was no computer involved. And then you have scientific computing, right? So you have all these different methods, FEM, molecular dynamics, all these different methods that developed the first 2 decades after computers found their way into scientific communities. But the important thing is about 50, 60 years later today, computational studies are sometimes in some fields dealt with as the gold standard. Sometimes even experimentalists would look at computational results as the benchmark. We believe them because they're tested rigorously and robustly. And they've become a major pillar of our community in terms of scientific endeavors. The interesting thing is deep learning has been around almost around the same time. So the first paper on deep neural networks goes back about 60 years. The first physics-guided neural network was developed about 35 years ago. So we even knew how to put physics into machine learning 35 years ago. But why is it that only over the past few years we are seeing an explosion, if you will, of this field? There are two, three main reasons, in my opinion. One is our ability to collect and handle large amounts of data. 30 years ago, it wasn't that way. And the other thing is, I think one particular set of methodologies that change the way we look at machine learning in science and engineering is this paper by Rheology and Karniadakis, where basically started or inspired a lot of work that has to do with putting differential equations into neural networks. And once you put in differential equation into neural networks or machine learning, your machine learning platform is not a black box anymore. And you can, to a good extent, know what's going on inside of it. And that has inspired a lot of follow-on work, and there is much more development here. So the funny thing is, this paper comes out in 20, I think 18 or 19. I think it's already been cited about 16,000 times. So you can imagine the effect it's had on many, many different disciplines, way beyond just fluid mechanics, where it was initially developed for. In terms of rheology, there's been a lot of work. And again, this is just a very small summary of what's been focused on in our community. But I look at it from different classes. It's because there are two different ways you can look at machine learning techniques in terms of methodology itself or the application. So this is more about applications of it in rheology, and this is focused on applications. You can always um, tailor machine learning platforms to model flows. So there are a bunch of papers cited here where you're trying to, using data-driven models, model a specific flow, complex flow, non-Newtonian flows. You can use machine learning for automated data handling or high throughput experimentation because now using robotic platforms, for example, you can do high throughput experimentation. Now, how do you make decisions about those data? How do you handle them and things like that? There's been some interesting work in rheology as well. There is material modeling and characterization, and by that, usually you're, for example, trying to predict the viscosity, trying to predict certain material properties at a certain condition based on previous observations. And then we have done some work on model discovery and other people too, where for a specific complex fluid, you're trying to use machine learning to discover models. So these are four different major categories of machine learning in our community in terms of applications. There are more. One is specific one that I'm not going to focus on today, and I think it's one of the biggest places where machine learning can have an effect is accelerating simulations. So anything that is repetitive and sort of based on simple principles, machine learning can learn and can speed it up. So there is a lot of effort in different communities in trying to speed up and scale up simulations using machine learning. I'm not going to talk about those today. If you want, this is, and I call this a semi-recent review, but this is a recent work a few months ago from us in current opinion colleague in enterprise science. We try to sort of categorize different data-driven techniques and talk about perspectives of where we're going with this. And I call it a semi-recent because, from then until now, there's been a lot of work coming out as well. So not always easy to keep up with the pace of developments in the field. So the first category of models I'm going to talk about is what is basically developed after PINs, physics informed neural networks. We called it RINs, or rheology informed neural networks, because the models we developed or we cared about were rheologically inspired, or rheologically relevant. The general idea is that you have a neural network, you have your input parameters. It could be, for a 1D system, you have X and T, position and time, and your outputs are, for example, velocity and stresses at different positions. And using automatic differentiation, which is the key to putting differential equations into neural networks, what you can do is you can get differential form of all these variables with respect to one another. And once you do that, you can basically set in rules of where you want your equation to favor, for example, to converge to a certain solution of a differential equation. And in science and engineering, pretty much every equation we care about is in form of differential or integral. And the reason is we usually care about flux of one variable with respect to another variable. So once you do that, once you're able to put in your differential equation, then you can put in basically any considerative relation that you want into your machine learning. So the general methodology is that you have a bunch of loss functions with respect to boundary conditions that are initial conditions, and then you have loss functions with respect to your equation that you're trying to converge to. And the total of that gives you a total loss, and you're trying to minimize that, which basically means you're solving that set equation. So we did that a few years ago. When I look at it now, we've gone way beyond this, but at the time we were ecstatic that we can do this. So this was work we did with my former student Mohammed Amin, and George Karnidakis was a collaborator on this work. We called it NNPIN, or non-Newtonian physics of neural networks, where, for example, you're now looking at a simple channel flow. Here is Poiseuille flow. This is a stress growth. And what you're looking at is as a function of time. You can think of it as a function of a strain. Doesn't matter. This is a Maxwell model. So you can pick any model you want, any form of differential equation that you want. And so on the left side, what you have on this column is the numerical solution, the exact solution of flow in that given geometry. And the middle is the data-driven solution, so the rinse solution of it. All we have done here, and on the right side is the error between the two. It's about 2% at most, so we're doing a good job. And so we did that in a couple of different works, and looking at viscometric flows and others, different geometries. And really, what I'm showing you here is that neural networks can be the counterpart to your MATLAB code. So if you use MATLAB, for example, to solve a set of considerative equations, you can equally use neural networks or pins that have embedded in them those differential equations. That's perfectly fine. And you're going to get a pretty good solution. Now, why would you want to do that? If you're just solving a set of differential equations, maybe you don't. Maybe MATLAB is still better. There are advantages. One is that these are generally easy to implement, and they're fast. The other thing is, which I think is more important, is that these type of pins are not as strictly dependent on well-posed initial or boundary conditions. It doesn't mean that you can get away with anything, but numerically, if you're solving a set of differential equations, you're strictly bound to have well-posed initial and boundary conditions. Otherwise, numerically, you cannot integrate in time or in space the variables you're trying to solve for. But in these neural networks, they're solving something basically by inference models, Bayesian inference or other types. And as a result of that, you're not really solving something, you're making these statistical predictions. So sometimes you can get away with not having well-posed initial boundary conditions. Have we checked it? Not really. The only thing we did was at the time we checked, for example, giving data in an inverse solution for a flow that had wall slip that we didn't know, and the neural network can recover for you the wall slip that was put in without knowing what it was at the beginning. So that's one way of putting just, differential equation into machine learning. The next one, go ahead, Michelle.
Well, it's not actually from me, the question, it comes from the chat. So
Sure.
I'm just
Go
gonna
ahead.
read it out.
Yeah,
So the message is, from my very little experience with pins, when I trained on a physical problem and simulated that problem, I got good results, but it got worse on very different flow conditions compared to training. What is your experience on this?
I wouldn't. So much more details is needed for me to know what exactly what kind of condition we're talking about. But when you're simply doing differential equations with pins, there is really no training. You're solving a set of differential equations. So it's not like you're training on a certain geometry. Um, if you're doing a full flow simulation, it's a different thing. Um, Pins do come with their own limitations. There are fragile time to time, and there is a lot of detail that I'm not talking about. What are your hyperparameters? What are your activation functions and things like that that we're not getting into here. And it's not like you're going to solve a set of differential equation for a given condition and then simply using the exact same conditions and hyperparameters you can transfer now to a completely different one. You may have to fine tune a few things, but in general, I would say solving for just differential equations in a forward fashion, meaning you're not recovering parameters, you're just solving a bunch of differential system of equations, you should be able to solve them using pins for different conditions, and it shouldn't really be that fragile. But again, happy to discuss details of what that condition is. And again, there is not a lot of training involved in just solving differential equations with pins. Okay, so this is what I call explicit um, physical embedding into neural networks, the first one that I showed in differential equation, because you're literally saying, this is my equation, I want you to favor this equation, right? But you can also do this implicitly. And the way we have done this is using multi-fidelity modeling. This is a paper from George Karnidakis' group on multi-fidelity modeling, and these are dummy data. So what they represent is meaningless. It's more about the methodology. Imagine that you have two sets of data. On the left side, you're looking at something. The high fidelity is the set of data that you believe in, that you want to adhere to. But you only have a few points. For example, these red guys here are accurate. The function that you don't know is this black guy, right? And you can see the nuances in that. What you do have more abundantly is the blue guy, which is low fidelity, meaning the trends are almost there. The ups and downs of the curves are there, but they're not exact at all, right? So if I just do the training on blue, it's going to give me some prediction that is representative of the blue trends. But what you can do, or for example, on the right side, what you see is that the blue has a constant amplitude and a different frequency, but the red is changing in amplitude and the frequency is different, right? The multi-fidelity approach allows you to mix the training of the two levels and make predictions at this pink level without really having a lot of red guys. So what does that red and blue mean in your own, respective problems? For example, maybe I have rheometry data, experimental data that I really believe in. I've tested my material, right? And then the only thing I know is that there is a yield stress in this fluid. So I'm gonna pick like a Bingham fluid or a Hilscher-Balkley model as my low fidelity prediction of that behavior. And using a Herschel-Balkley or Bingham model, I can generate ton of data, right? I can generate ton of blue guys from a simple model that only has a yield distress. It's not accurate, but it has the physical essence of that fluid, right? Those are not accurate. Those are not measured. Those are not high fidelity, but they still have they carry some sort of physical intuition about the material that I'm trying to predict, right? And then I mix that with the actual experimental data and I can make predictions. The way you do this is in a two-step process. So I'm going to explain what the material is, but really what you do is at the low fidelity, so you break your neural network into two steps. The first step is your low fidelity. So you're using those, abundantly available data to train a neural network. And then the output of that neural network at the low fidelity level becomes input to your secondary high fidelity training sets. And in our work, we did it in two different steps of a linear and a non-linear neural networks. The linear one is very, very simple. The non-linear one usually has more layers and is a little more complicated. But the general idea is that the output of the low fidelity become input to this, and overall together they make a predictions. We initially published this work in Journal of Rheology. This was our very first work in machine learning. But then we wanted to explore this idea of, well, the first work was only on a steady shear viscosity of a shampoo, Head and Shoulders shampoo, because the work was supported by Procter and Gamble. But then we wanted to explore the idea of transient rheology data that are more complicated. And also this idea of what if I don't know much about the physical intuitions of the fluid to begin with. So the experimental data you're going to see is from the group of Norm Wagner and University of Delaware, and this is work that my former student Milad Saudet did. This time we also picked a shampoo, Johnson & Johnson shampoo, and the reason was we wanted for anybody to be able to basically buy the same product and do the same experiment and get the same result. And the general idea was, what if I don't know a lot of physical intuitions about it? So here is what we are doing. This is my high fidelity data. And this is not in the form that you're familiar with, but bear with me for a second. I'll explain what this is. We have basically this shampoo. We are looking at a steady shear viscosity, so flow curves, right? At different temperatures and different shear rates. And this is a very simple fluid. So you're looking at a shear thinning fluid with a zero shear viscosity. You're going to see it in a different form that is more familiar to your eyes. But we're looking at viscosity. You'll see, again, the actual values in a second. But this is how my high fidelity data looks like. So what we're doing is we grab this data. So Norm sends us this data and says, these are 5 different temperatures and a bunch of shear rates. These are steady shear viscosities. We don't pick a model. What we do is we use a simple linear regression on the actual data. And then basically this is just a curve fitting, right? So you get the data, you fit a curve that explains the data, and that curve fitting can be completely dumb, completely mathematical. But now, using this low fidelity, imagine if all across this space I have maybe 30 data points. Here I can make 30,000 data points because this is just a simple curve fitting and I can just generate as many data as I want. And I'm going to call it low fidelity. It's made out of high fidelity, but it's not really measured. And you can see the trends are completely different, right? In this case, because we're simply using a linear regression, what you're getting is a simple power law. So with mixing the two, the resolution you have for the multi-fidelity prediction is like this. Now, at any given temperature and any given shear rate, I can make predictions. It's not jagged anymore, like you're seeing here. Now, how does it work in action? So this is, again, the more familiar set of flow curves. You're looking at steady shear viscosity as a function of shear rate, right? And you have different temperatures, 10 to 50. When all the scattered data, anything I'm going to show, all the scattered data are the actual experimental results. When they're filled, like 10, this one is 30 and 50, they've been used in the training process. When they're open, they haven't been used in the training process and they're test data. So they're not included in the training process. The lines are the multi-fidelity predictions. So basically, if I start from these three lines, right, the 10, 30, and 50, fit basically a line to it and generate a ton of data at different temperatures and different shear rates, and now mix the two, I can make pretty good predictions at 20, 25, and 40 degrees. Okay. This is what we call interpolation because what you've observed is 10 degrees, 30, and 50, and you're asking for temperatures in between. What's interesting is what you can do is extrapolation with this without, again, knowing anything about the physical principles that derive the rheological behavior. So this one, for example, we mask the 50 degree Celsius data, and this one, the 10 degree Celsius data. And we used everything else. It looks like even for those, we are able to make predictions at a pretty good level. So we are doing good predictions for systems that are outside the observations during the training. Okay, so this is steady shear data. I said we wanted to stretch it and see if we can do nonlinear data. The interesting thing is you can. So this is the same thing. This is just one of the temperatures, but now you're looking at different shear rates. You're looking at a stress growth. I'm showing it as a function of time. Usually it's as a function of strain, but you're looking at a stress as a function of time when you apply a constant shear rate of 0.05 all the way to 100 reciprocal second. And again, the same thing. When open symbols are shown, then that means that data was not used in the training. The filled symbols were actually used. And what you're seeing is the typical nonlinear behavior, right? The initial elastic response, the stress overshoot that you get. This is the nonlinear viscoelastic regime. And then what you reach is the steady state that you saw in the previous slide. What's interesting is you can also predict these, right? And again, interpolation and now extrapolation, right? At the lowest and the highest shear rates. So what's interesting is without knowing any physical intuition about the material, but just using one set of data, but doing it in multiple steps, you can make pretty good predictions of the physical behavior, both in a steady state and in transient regimes. Um, what I'm not going to show, but it's actually in the paper if you wanted to take a look, is that it breaks, right? A model is only good if it actually breaks at some point. So this breaks down when you go, for example, to predicting small to large amplitude oscillatory shear data. And then you actually need to inject some physical intuition. You actually need to give it a model that is descriptive of the behavior. Because it's not, so this general idea of just using regression to get a curve fitting is not going to work. And at some point, you really need to know some physical intuition about the material. So this is the implicit way of putting physics into your machine learning. And I showed at the beginning the explicit way. Michelle, go ahead.
I'm sorry, maybe I missed
No,
it, but what was the low fidelity data you used here?
Yeah. So this is again the high
It-
fidelity data is these symbols,
No,
right?
no, I mean for this case, I get it for the linear one, but for the non-linear one, was it the
The
same
same
approach?
thing,
Okay,
the
okay.
same thing. You're using basically this line, and these three other lines. So basically, I'm using in this particular case, one, two, three, four, five different shear rates, this filled ones, as my high fidelity. I fit a model to it, and I now generate a lot of low fidelity from those fitted models. Yeah,
Thanks.
sure. So the next step was actually the work we did 3 years ago in collaboration with Simon Rogers. And the idea was this. And so this was actually the very first thing that got me sold on this idea of machine learning. I had a chat with George Kaniadakis a number of years ago, and he's an applied mathematician. And what he said that completely changed my view was this. He said, if you get a set of differential equations and you solve them today, or if you solve 50 years from now, the results are the same and should be the same, right? So any measurement, any experimentation you do does not change the result or predictions of that differential equation. What if I have a model, but I'm making measurements, the actual measurements from a material that should make my predictions of the behavior better. Every single experiment should make everything better. So this goes back to that idea. I showed you the implicit and explicit physics intuitions. The good thing is they're not exclusive, so you can mix and match. And again, each new measurement should make the model better. So this idea that I have a model and I have experiments, I should be able to mix them and basically make a hybrid multi-fidelity based model on experimentation, and but they're also informed by descriptive models. So I'll explain what I mean by those. So what I'm going to do is I'm going to team up with Simon and his student, Krutarth Kamani. We asked for complex rheological data. So what we got was these. You're looking at a fumed silica gel at an intermediate volume fraction. So the details of the system doesn't matter, but what you can see here is that you're looking at two different applied shear rates at different weighting times. These are thixotropic materials. So once you set them on the rheometer, the different times you give this material to form internal structure will give you a different initial condition. So these weighting times, as you can see, will change G prime, meaning the shear modulus of elastic modulus of the system is actually growing over time because now you have more and more structured material. You have two different time scales involved because you're seeing a two-level yielding in this material, right? And then you have this plastic flow at the end, which is basically the overall behavior is very similar to a TVP, thixotropic elastoviscoplastic fluid. If you look at a small to large amplitude oscillatory shear data at different frequencies, you can see a pretty diverse set of behavior. You can see this typical curves that are representative of the TVP behavior. So these are complex. We wanted to see if we can model this. Okay, so what we did was initially I asked for only a small subset of this data. So let me take a step back and explain what kind of model we are using as the descriptive model. So this is isokinematic hardening. This is developed by Garrett McKinley. This is by not at all the only model that can describe this set of behavior, but it's one that I'm very comfortable with and I really like. So we use this model a lot in our group. This has four different elements in its construct. You have this viscoelastic element, and then you have this plastic element that has the kinematic hardening idea and the back stress. So this is coming from the Boeschinger effect and the idea that shearing in different directions will put a back stress on the material. You have this sliding block that has a plastic behavior. And by combining these, you have basically three different coupled differential equations. One that shows you the level of microstructure, one that gives you the level of back stress, and the other one, the overall shear stress. Okay, and you have to solve these three together to get the overall behavior. So what we did initially, we only got three sets of data. Reciprocal, applied shear rates of 1, 10, and 56 reciprocal seconds at three different waiting times, right? So these three sets. We basically used pins with IKH to recover the parameters of IKH because there are about 9 or 10 different, depending on the version of IKH you use. There are 9 parameters in this model you have to recover. And from those three sets of data, we use basically our pin as a glorified curve fitting to recover those 9 parameters. And now I'm solving those three coupled equations to predict what the behavior is at different waiting times and shear rates. And this is the dashed lines are the typical behavior that you get. So what you're seeing here is that when you start from three sets of observations, you can make pretty good predictions with respect to the final steady state. It's off a little bit, but it's not that off. But the transients are completely off. Your G, for example, is pretty good. So you're recovering a very good elastic modulus, but everything else with respect to the time scales involved with the process are completely off. And there are fundamental reasons why. We can discuss that. Let's not get into it right now, but the general idea is that just one length scale or time scale is not enough to predict this set of behavior. You need many more elements in there. And the more elements you put in, the more components you have in your model, you're easily now at maybe 15, 20 different model parameters, makes things a little more complicated. Okay, because now I'm solving just set of coupled ODEs, I can make predictions for any given flow, right? So the black here is the experimental results of a small to large amplitude oscillatory shear. The red are predictions of this IKH, the same as these dashed lines. I'm just showing now everything in red. And what's interesting here is that we are off, right? We're doing a good job maybe here at large amplitudes and large frequencies, but we are doing a terrible job on pretty much every other range, right? But now comes this idea that I told you at the beginning. Well, now I can generate a lot of data, right? And use them as low fidelity because they're coming from a model that is descriptive of the overall behavior. They're not exact, but I can generate as many data as I want, right? So I'm going to use all of these red guys now as my low fidelity and go back to Simon and ask for three more sets of experiments. So I'm going to ask for three of these black guys and use all the red to make predictions. And the type of prediction you get is now this. So your green now is the multi-fidelity approach to this, right? So now you're using every experiment to do a little bit of better predictions. So this is what we call at the time a digital rheometer, because at a certain point, you've learned enough flow curves, you've learned enough flow protocols and responses that you don't need to do rheometry anymore. You can now make predictions. You have a model that describes the system, and then you have made handful of experiments that are used in the training, and now you can make predictions. What's interesting is you can use pins, and this is relevant to rheology very, very much, but not a lot of people use it. Fractional derivatives. So this is a very, very quick background on what fractional derivatives are. You're looking at, so if I look at a function f of x and, df dx would be your first different derivative of f. You can get the second derivative, but you can also get a fractional non-integer different derivative of f with respect to x. Why is that important? Because think about a stress and a strain for a second. Stress follows the first derivative of a strain or gamma dot in a viscous fluid and follows the zeroth derivative of a strain or gamma itself in a solid. And for any viscoelastic fluid, it's in between, right? So you can now, instead of using a spring and a dashpot, what you can use, and it's shown in these A, B, C diagrams here, is what we call a spring pot that is fractional derivative of a strain. Okay, so using that, it's a very, very powerful method of predicting behavior in a concise and compact fashion. What you're seeing, for example, here is a fractional maximum model with a solution of alpha and beta as your non-integer fractional powers. And this is what we call a fractional Kelvin-Voigt model. This work we did, and my student Donia did in Rio Acta a couple years ago, showed that you can use pins to recover any given fractional considered model and solve for it very, very easily. The good thing about that, if you've worked with fractional models, you know that numerically they're not easy to work with. And and maybe one of the reasons many of you may not even have heard of them is exactly that, because they're not easy to work with, but they're really powerful. Anyways, but more importantly, once you write a fractional model, as soon as you put the power to an equal to a negative number, now you're doing an integral, which is generally something that neural networks are not good with. So the follow-up work we did, and this came out a couple months ago, was actually doing integral functions with pins. Anyways, not getting into that, another thing you can do, and again, because we are talking about different sort of applications of machine learning and rheology. The other thing you can do is you can actually put the material in the driver's seat, right? And put the data in the driver's seat without choosing what model describes the data. What you can do is you can build a library of different consider models. And for example, 2 weeks ago, I was in a viscoplastic fluid workshop, and there's always this discussion of what is the best model that describes a viscoplastic behavior? What kind of a model should I use? Should I use a Saramito model? Should I use an isokinematic hardening model? Or maybe a completely different one? And maybe the reason is, maybe the answer is, well, you don't choose. Let the data choose. So for example, here we are looking at a steady shear viscosity, the scattered data points, and we have all these different consider models embedded into the neural net. And you're asking, what is the model that describes this data best? And it actually can give you a pretty good answer very quickly. So the overall behavior, the overall sort of guideline that we had to digital rheometry was sort of like this. You start from a limited number of experiments, you do automatic model selection. So now you know what model describes that data. Now you can use that pin to make any number of predictions using that model. So that's your MATLAB code step 3. Now you can, because now you have a lot of predictions, you can construct this multi-fidelity scheme, and you can add a little bit of more experiments. And then at that point, you can drop the rheometer and make predictions at the level of, the physical measurements. All of these, to a large extent, assume that a descriptive model actually exists. What if there is no model available for that given material? What if I'm starting from something that is completely unknown to me? I do a little bit of testing, and I just want to use data-driven techniques to teach me new physics, to learn about what's going on inside the material. You can do that too. We used Cindy or this is sparse identification of nonlinear dynamics using machine learning. The general idea is this. You have, again, your input and outputs. This is, for example, strain and time. Your output is stress. And then what you can do is a two-step process. You can build a library of candidate functions, all of the stress components, their first derivative, second derivative, also first and second derivative of the deformation itself, and their products. In the first step, what you're asking is to identify the eigenmodes, or the most important candidate functions that describe a behavior. In the second step, you're finding the coefficients for it. And by doing that, what's happening is you give it a set of observations, and you're asking, what is the dynamical system that gives me this set of behavior? So what you're seeing here is, again, a collaboration we did with Simon Rogers. And we wanted to do this for a viscoplastic fluid. So these are the experimental measurements we were given. You're looking at a small to large amplitude oscillatory shear data for a carbopol 980 solution as the model complex fluid. This is, again, something that is very commonly used as a viscoplastic fluid. We make no assumptions. We just put in those candidate functions into the library, and basically this is the type of model that you recover. So the Cindy, or again, we called it Rents here, but really this is just a Cindy, gives you a dynamical equation. So this is sigma dot as a function of sigma itself, gamma dot, gamma double dot. So what is new here? This is very similar to nonlinear viscoelastic equations that are out there, and you would see them in textbooks when you simplify it. But what's very interesting is this component, C5, gamma double dot, gamma dot. You usually don't see that component show up. So the interesting thing is that the neural net is telling me there is this component that may be important in describing the physical underpinnings of an observed set of behavior. So maybe I should look at a set of components that I haven't before. So it's in a way teaching me new physics about this. But anyways, so I have this model. How does it work? So this is the model predictions for these set of data. This is the model that Simon's group came up with a couple of years ago in PRL, explaining the same set of experimental observations. So what you can see is that our model with one shot is actually doing a better job in predicting the experiments than the model. You can say, well, this was the set of data that you recovered the model from. What about other flow protocols? You can actually do a decent job on creep, on a steady shear, on a step shear. We tested it, and it's thermodynamically consistent. All of those things that you care about when you construct a set of considered models. Okay. Okay, so this is model discovery. Very quickly, because this is the more exciting stuff we are getting into more recently. These are what we call DPONet and FNO, or neural operators in general. The general idea is sort of simple. What I've shown you so far is when you go from x to f of x, right? And that is a function. When you go from x to f of x, you just need a function f to be basically predicted, right? Or approximated. Now imagine I'm going from this space of the red guys here to this space of the blue guys here. So I'm, instead of going from one data to data, which means function, I'm going from a function to another function. This is called an operator. So when you, instead of approximating a function, you approximate an operator, you're going from one functional space to another functional space. So why are we doing this? The reason is simple, but I'm going to show you two different ways. What is, again, what we call FNO, Fourier neural operator. The other one is called deep operator network. The foundations are exactly the same, but they both work in different ways. One work in a Fourier space, the other one basically decouples your data into basically branch and trunk. That doesn't matter, but here's what we actually do for operator learning. And this is the work of my former student Milad and former postdoc Deepak Mangal. So imagine, again, going back to TVP fluid, this is my coupled equation for stress and microstructure parameter lambda. There is a buildup parameter, there is a breakdown parameter, and then for your stress reads basically the microstructure at any point, shear rate. There are multiple parameters inside to give you a given response. Or a viscoelastic fluid. This is a tensorial Giesecke fluid. So this is a 2D. You can easily make it a 3D. Doesn't really matter. But now we are looking at something that has normal stresses involved. Okay. So what do you do in this training for training neural operators is this. You make, using Gaussian random fields, what you can do is you can make a function of gamma dot, put it into this equation, and recover lambda and sigma, your microstructure and shear stress. And what you're learning is what is the operator that takes you from the left to the right. So this is the operator that, if this was a function of shear rates, would give you the stress. Okay. Do the same thing for Giesecke, but now you're doing this for different components, obviously, because you have different components of the formation tensor, you also have different components of the stress tensor. So you're doing basically a bunch of functions as input and a bunch of functions as output. How do you generate them? Randomly. You randomly generate the left-hand side of these two, and then the solution is really putting those random functions into these two sets of considered equations to get a stresses. Once you do this training, now you're asking, what is the result of a steady shear, step down, oscillatory, or any arbitrary flow that are not exactly observed by the neural operator. And what you're seeing here is that the exact solution, the physics-informed deponent, physics-informed FNO, and FNO are exactly on top of one another, meaning they're all predicting the same thing. So I've done enough learning that I know exactly if this is my function of gamma dot, this would be my response for sigma. So why is this interesting? So that was the TVP. This one is for Giesecke's fluid for planar extension, pure shear, simple shear, and again, arbitrary flow. You can predict sigma. You can predict N1 is on top, sigma, shear stress is on the bottom. So you can actually make really, really powerful predictions using neural operators about any given viscometric flow. But this is not by itself super interesting. Again, so this is, if you want to read more about this, this was published in Journal of Rheology earlier this year. What we're doing now, and we're really excited about, is the work that my current student, Mada, is doing on using transformers. And so if you're familiar with transformers, these are the T in ChatGPT, right? GPT is generative pre-trained transformers. And transformers are the type that are traditionally built for natural language processing. But what you can do is you can actually embed neural operators into transformers. So what I'm going to show you here is very quickly the result. This is work in progress. Hopefully we'll get this out soon. But what you can do is you can actually do full flow modeling. So this is a ground truth numerical solution, finally resolved CFD, a viscoelastic, basically this is a Giesecke's fluid undergoing this contraction. This is a canonical 4-to-1 contraction that is usually used for viscoelastic benchmark. And on the bottom is the prediction of our transformer model. And you can see the match between the two. Are we off in some places? Yes, absolutely. But imagine that now you have a transformer model. So these are generative models that actually can do pretty good educated simulation of non-Newtonian fluids, right? And without really doing, once you have enough training, you don't really need to do CFD anymore. You are now predicting velocity fields and pressure fields in any given channel. So we are working on this. Just give you a little more example. This is Oldroyd B model. So this is, you're looking at velocity in the X direction, the shear direction. And this is the velocity gradient direction. So you're seeing basically, again, for all of these, the top half is the ground truth, the bottom is prediction. You can actually use these transformers to accurately model non-Newtonian fluid mechanics. And then you can get crazy with the geometries, flow past the triangular obstacle for an Oldroyd B fluid. And you can see that the model actually does a pretty good job. The video is unfortunately a little jagged and in full screen mode. I don't know why, but it's actually much smoother. We're doing a good job in predicting the flow behavior, right? And in all of these, you're looking at a prediction that has not been observed during the training. So none of these were observed by the model, but now you have transformers that actually can do full flow modeling. So with that, I think I'm over time. So I'm going to just summarize here. This general idea of what I call rheoinformatic and, using machine learning for rheology. It's really powerful. You can go from formulation and synthesis to rheology. You can do model detection, characterization, and construction, as I showed you. You can do accurate rheology prediction, and then you can do complete modeling of any non-Newtonian flow in given geometries. All of those under this unifying umbrella that brings experiment theory and computation together in a seamless way. Now, are we there yet? No, I just showed you snippets and purposefully very, very successful snippets of those works. But I would like to remind everybody that it took about 60 years for computational sciences to get here, right? We are only working on this for the past 4 to 5 years. So give us another 4 to 5 we may actually make a difference, right? So with that, let me thank my group. These are the most important people that actually do the work and I take the credit for. This is a recent photo of the group. So this is Donia, who's done some of the work that you saw. This is Mad. I'm not sure if anybody else that was involved with this project is in here, but former student Amin Milad, former postdoc Deepak also significantly contributed to what we know about these systems. So I'll stop here. I'll try to answer questions and I'll stay available for long periods of time, as Leah suggested, for follow-up questions.
Thank you. Thank you so
Thank
much.
you so much.
It was really great.
Of course.
Questions, people. So
Yeah. Yeah, I
go
can
for
see
it.
also we have some people, Hugo, Vincent, they are working on machine learning on EFD, so I guess they have questions. Or yeah, there are many people. Hugo, Vincent, you don't have any questions?
Please don't be shy.
Yeah, don't be shy, that's fine.
And if you
They
are,
do
you
that
can
on,
write it in the chat.
yeah, you can write in the chat. They're doing stuff like that. I don't really know their work, but they were doing some simulation on blood flows in the brain. So that might be interesting too. And one of them is also working on eventually the taking into account the red blood cells and so on, what happens with them. And eventually they have questions. I don't know about that. There is one question. My microphone is actually broken. Sorry. That's fine, Hugo. You can write in the chat the question if you want to. But I was wondering, did you try also with suspensions or granular flows or anything related to that?
Yeah, absolutely. So what I didn't show, this is more recent work of this lady on the
Yeah.
bottom. Saw that? She's working on non-local granular fluidity models, both in forward and inverse solutions. So this is, I'm a fan of the model Ken Cameron developed for non-local granular fluidity. And so, for example, this idea that if I look at a velocity field and or a flow of a granular packing, can I basically recover all the model parameters to then be able to predict the flow of the same granular packing in different geometries, right? Um, so numerically, I can tell you that it's a resounding no because there are so many different parameters that go into that model. But it seems
Mm.
like data-driven models are actually doing a very good job. We have had some success. We're working on it, but that's what we have done in granular systems. Not really on suspensions because I've
Yeah.
done enough work on dense suspensions and shear thickening to know you don't want to start anything with dense suspensions. That's the beast you wanna attack at the last
Yeah.
level.
Yeah, I could
Good,
imagine so.
good to
We have
know.
one. Yeah, good to know. There are some questions in the chat actually.
Yeah, absolutely.
So there is Joshua that is asking, how sensitive are these fitting modeling efforts to the presence of noise, like systematic or random in experimental data?
Uh, Great question, Joshua. They are very sensitive, right? Depending on, well, I should be careful because I described a couple different things, right? The transformers, neural operators, and then the pins. They are in general all sensitive, right? We haven't done a good job, admittedly, on uncertainty quantification, and I know you have. You have done a wonderful job in terms of, for example, model detection using basically Bayesian inference models and uncertainty quantification. Same things should be applicable here. We haven't done a good job in them, so if you have good ideas or would like to collaborate on some of these, please. Um, in terms of noise, in most of the works I showed, we do a systematic study of adding noise to the data and see where the model breaks down, right? And at some point, they all break down. But specifics really depend on what example we are talking about. For example, with shear, simple, steady shear viscosity data, it's less sensitive. As soon as you go to something like a Laos data, you add a little bit of noise, it throws you off completely, right? So it really depends on the complexity of the data or the behavior you're trying to model. I don't know if that answers your question.
Yeah, I can answer it here. I'm just a simple experimentalist, so sorry about that. I haven't done any modeling like this myself, and maybe you've confused me with someone else. I'm just wondering, like, what should I be careful about in
Hmm?
doing an experiment to avoid polluting the data with stuff that is going to really throw off models like this, right? What are the critical things to avoid? Like, I think that from my perspective is a very important thing to know. Like, should I
Okay.
care particularly about baselines, or should I think about noise, or should I think about offsets, or whatever there may be, right? There's always stuff in experimental data that you don't want.
Sure. Yeah, that's a great question. I think there are works out there by Randy Ewalt and others where they talk about how to filter out bad data, for example, right? We haven't done work in that direction. Um, but really, on the machine learning side of things, data is data. The model doesn't know which one is a good data, which one is a bad data, and what are the noises involved. It's going to use all the data you're going to give it, right? Um, so I think that's exactly where the domain expertise and the experimental rigor will always need to be there. So as we go through these high throughput automated systems, we want to make sure we always are generating actually good data. Um, Repeated experiments, making those are reproducible, always a good idea, right? But on when you're developing these models, the model deals with these data as data. It doesn't really understand where they're coming from. So they, at least I'm not aware of too many different models where they can actually pick out bad data.
So if I can ask another question about this, then like um, forgive my ignorance here, but for example, when I do a fit, I
Hmm.
can add weights to the data, right? Because I know that some data is maybe less trustworthy than other data. This is actually what we teach the first years, how to do that. And I would hope that, in maybe future versions of this kind of modeling or machine learning efforts, you could do something similar, right? Is that possible even?
Absolutely.
That would be my main
Yeah, absolutely.
yes
No,
to
that
do,
that
right?
definitely is possible and it is something that we are doing. Where you have less confidence on the data, you can put less weight on it in terms of learning. So
Okay.
what you know is, for example, this part of the data I'm really sure about. I'm gonna put more weight in my loss function and in my learning process on that data where I'm more confident about. So you can do localized weight functions in your learning where on based on the confidence you have in the data. For example, if I'm looking at a yield stress fluid, Leah gave the example of blood, right? So it's we all I think agree that blood is a yield stress fluid, but the funny thing about that is the yield stress is very tricky to be measured for blood. So everything we have done on experimental data on blood viscosity has failed so far because the confidence level we have for low deformation rates is very low. Um, you get, I don't know if that answers the question. So
Yeah.
for my high shear rate regime, I have a pretty good idea of what the behavior is, and I can make predictions. For low, because the confidence is low, I'm not going to put a lot of effort in trying to predict something that is unpredictable, right?
Yeah.
So it goes hand in hand with the confidence level you have in the data for sure. And that can be built into the models.
Okay. Thanks.
Sure.
So I see here two more questions. One from the chat. I'm gonna go with that just because it came a bit first. So the question is, I was wondering if on top of transformers, you're also using graph neural networks. Before using transformers, we started using GNNs, and they are very well suited to work
Mhm.
with meshes.
We haven't done GNN. There are a lot of good works out there using GNNs. Transformers, the advantage they have is that hopefully in the long run, they're going to be more generalizable. So imagine you're doing the training in one geometry and you want to make predictions in a different geometry. GNNs are not good with that. Transformers, because of this idea of self-attention, can learn basically the spatial configuration can be encoded in the training process for transformers. For GNNs, at least I'm not aware of methods that can do that. So we haven't done GNN. I know a lot of people have. At the moment, GNNs may be actually more powerful, but with the pace of developments with transformers, we decided to go ahead and use transformers actually. So.
Okay, thanks. And the person thanks you also. And
Gavin
yeah,
has
Gavin, yeah.
Gavin, go
Yeah.
ahead.
Hey, yeah, thank you for your talk. That was really interesting. I just had a question about Gaussian processes. So I was wondering if you had, it seemed like for most of your models, like say you had like a physics-based model, you would combine some, your standard DNN loss function with some physics-based loss function as well. Have you considered doing that with a Gaussian process instead of a standard deep neural network type model?
No, we haven't done that. And I would love to hear if you have suggestions of what that could. Well, we have done a little bit of work with Gaussian models on a very different thing. I didn't show because the project was unsuccessful, and maybe that's why we stopped working with them. Um, but can you elaborate on what parts of the neural network you're thinking about being replaced with the Gaussian models?
Uh, I mean, just kind of like entirely in place, replacing the neural network. So
Oh,
the
okay.
idea would be that you could combine this with like an active learning type framework, because in my area, like data sets are very sparse. So if you wanted to train a neural network, like your model has to be either super small or you're overfitting everything. So
Yeah, 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 yeah,
um,
yeah,
yeah.
absolutely. Um, no, we haven't, right? And I think part of it is motivated by the type of data we have, and everything we've done so far is, for example, there are a lot of good active learning methodologies. For example, when you look at turbulent modeling and just fluid mechanics, because the type of observations you have is very different with viscoelastic fluids, with non-Newtonian fluids, or with viscometric functions. Um, the parameter space or the entire phase space is not as crazy as turbulent flows, for example. And we haven't had that issue of having a very, very small subset of data that we needed really to use active learning for. Um, so I'm not personally super familiar with different active learning methods, but I would imagine that there are scenarios where those would be much more powerful for, of course.
Okay, cool. Thank you very much. That's helpful.
Thank you. Looks like
Yes,
Vincent.
Please go
Vincent?
ahead. Vincent.
Yes, sorry, I have a question which kind of is linked to what you were saying about the sensitive about answering the question about good and bad data and maybe weighing the data in while learning. I have actually have an application where we have really few experimental data, and so we are trying to make a model learn as well on these data and as well as in on numerical experiments. And I was wondering if you had any insights on how to combine maybe the learning on both these sources, because of course
Mm.
the numerical parts is built on hypothesis, and so I mean both sources have their pros and cons, but they are not really pulling the model towards the same uh, uh,
Mhm.
optimization, I'd say. So I was wondering if you have had any
So
sort
I
of.
would say if the type, well, if the input and output functions are comparable, meaning if your numerical and experimental measurements or the two sets of data are the same thing, for example, shear stress, shear rate, or anything given input and output, then I would go with something like a multi-fidelity approach. there are other types as well. I've seen people doing, for example, what we call sequential learning. You can do a one-step learning with one set of data, and instead of starting from scratch or zero, you're now starting for the second set of data with your, for example, do the first learning with numerical results and then add experiments. There are different ways to do it. I would say multi-fidelity modeling is always a very powerful method, and I really like it because we had really good success with it, but it's not the only way to do it. I would say sequential learning is also there. But if the type of data is completely different, meaning your numerical result is input and output functions are not exactly the same as the experiments, then what you can do is what people refer to as clip, meaning that you link the two learning processes together, but they're actually two different sets of data and two completely different measurements. There are methodologies out there that are more from computer science and computer vision community. So I haven't seen a lot of application in science and engineering. We haven't done anything. We definitely have interest in pursuing those, but that's the only way I can think of.
All right, thank you. And thanks for the great talk.
Worse.
Okay, so I do have one question, and it's actually a bit related to my work. And so I mean, you said it already that dealing with suspension is the final boss of the game, and I do agree. I mean, people may not agree, but I do agree with that. And I've recently tried to approach machine learning, doing actually the what you said at the beginning, the part that you didn't talk about today. So accelerating simulations. I don't know if you said it on purpose. If not, thank you. If yes, thank you even more. And but I don't want to necessarily talk about that. Let's suppose that you have a fully reliable data set describing local stresses in time. Okay, so the evolution of the local stresses, things you can retrieve from numerical simulations indeed. How feasible, and if feasible, how easy do you think it would be to get to the final boss of the final boss, which is get the constitutive equation?
Mhm. That's a good question. I don't know that I have a good answer to it. The hint that I have would go back to the work that Emanuele Delgado has done recently, and this idea that if you have fully resolved local stresses, they suggest that the overall macroscopic rheology can be directly linked to stress correlations in a space, right? And if they've done it for gels, for soft glassy systems, but not for dense suspensions yet. But the idea is that it could be generalized to that. And if that's the case, if that is the case, that's a big if, right? But if that's the case, if you learn these correlations throughout your domain, then you should be able to say something about your macroscopic rheology. So that would be my hint. We haven't done anything in that, but maybe.
It was mainly just like let's think about it together. Then
Yeah.
yeah. Okay. Okay. Thank you so much.
Thank you, guys.
Do we have any more questions? Okay.
Oh, and now I see I've got a couple of my students here. So Donia, Rob,
Nice.
and who else is here?
Well,
Mother is
then,
so some of them are here. Some of the culprits of the work that you saw today are actually here. So shout out to you guys.
well, if you hear us, thank you. Thank you for
Yeah, thank you
nice
so
words.
much.
Yeah. They are indeed. This is for
Yeah.
young rheologists, so they are
Yeah.
it's thanks to them and for them.
Mm.
Great. Okay, then I'm gonna stop the recording here.